Hey folks, welcome back to another video of the system design playlist. So today we are going to discuss about the database indexing. And then first we will cover the introduction part of what is database indexing, what exactly database indexing with examples. And then we are going to discuss how database indexing works, right? And what are the benefits of database indexing and what are the data structures which are used for indexes, how to use them, and finally the summary. First, let's talk about the introduction. So let's consider a book. There is a book of 1,000 pages. Let's say there is a book of 1,000 pages, right? So suppose you are trying to find the page which contains information related to certain word. Suppose you are searching for some word, right? So without the help of an index, let's say your book doesn't have any kind of table of content, or we can say index. It doesn't have any index. What you will do is you will search entire book. You will search entire book, all the pages, and you will try to find the word in each and every paragraph and each and every line, right? But with the help of indexing, within order of 1, you will go to that index, and based upon the word you will find the page number. You will find the page number and go to that, right? But if you don't have the index, you have to search all the way. Like you have to search each and every page according to the word, and it will be like time complexity will be order of n. You have to go n times, right? But with the help of an index page, you know where to look. So once you find the right index, you can efficiently jump to that page. Exactly. And the index, since it is sorted so alphabetically and gives number for a specific information, this saves us from spending too much time flipping every page. That's all about it. Now let's talk about the introduction further. Let's talk about the formal definition. So database indexes work in a similar manner. Like they guide the database to the exact location of the data, and they enable faster and more efficient data retrieval. Like suppose you are having some record. Let's say this is a table. You are having some record here. Okay. So this is index 1, this is 2, this is 3, this is 4, and this is 5, let's say. If you don't have the index, let's say this is the index, right? If you don't have the index, what you will do, you will search here as well, you will search here as well, here as well, here as well, and here. But if you have the index, you will directly, let's say you have the index and your data is available in record 2. So you will go to 2 directly and you will find something here, right? That is the use case, and that is why we need the indexing, to save our time, to save the retrieval of data. Like efficiently we can retrieve the data, and it will enable a faster way. So like in this video what we are going to cover is we will explore what are database indexes, how do they actually work, and what are the benefits of using them, different types of indexes, what data structure they use, and how to use them. Now let's continue with the discussion. What are database indexes actually? So suppose you are having an index table and you are having a database table. In the index table, what do you have? You have the key and you have the pointer. Pointer is pointing to some location in the data table, right? So a database index is a super efficient lookup table that allows a database to find data much faster. How you are finding data much faster? Let's say I am searching for a particular record. I go to this key, right? It already has some pointer which is pointing to the record. It is pointing here. So instead of going to entire table, right? Instead of going to entire table in finding the record, I will simply go to this row and search for the record. Search for the attributes which I need, right? So it holds the indexed column values along with the pointer to the corresponding row. in the table. Without an index, the database might have to scan every single row in a massive table to find what you want, which is really a painful, slow process. So, but with the help of an index, the database can zero on the exact location of the desired data using the index pointer. We are actually using the pointer. With the help of pointer, we are reaching to the location where we need to search our data. Let's say this is a record of a student. Let's say this is a ID, this is the name. Let's say this is the age, or we can say marks. We can also take marks here. Let's say I am searching for someone C. So I am going to check the pointer pointing to which location. It is pointing to this location. I came here. Now I needed the name. Let's say that there is name XYZ here. So within a couple of seconds, within very less time, within constant time, I am able to retrieve the data, right? This is what database indexes are. Now let's talk about how to create database indexes. We have discussed what are database indexes. Now let's talk about how to create them. So let's take an example of creating an index in a MySQL database. We have a query. Let's say we have a table named employees. This is a table with the name as employees. And this is the ID of the employee, which is the primary key. This is the first name, which is a varchar, right? Varchar means it is a string type. And then we have last name, which is also varchar of 50 characters. And let's say there is email of an employee. There is the employee belongs to some department, like if the employee is in management department or financial department, if that employee is in technical department, right? And the employee must be having some salary. Now let's create an index on the last name. Let's try to create an index on the last name column to improve the performance of query that frequently search or sort based on the last name. So let's take this query. This is a query through which we use the create index. Here we are using the create index statement to create an index. The index name is index last name, right, on the employees table. So we are using it on the employees table that we have discussed previous slide. The index is created on the last name column. So we have a create index query and it is working on the index last name, right? It is the table name, employees is the table name here, and this is the last name, which is the column, right? So after creating the index, queries that involve conditions or sorting on the last name column will be optimized. For example, let's say we are doing select star from employees. So what we are doing is we are selecting record of employees. We are selecting actually record of employees, and the condition is where the last name is equals to Smith. So if the last name is Smith, right, it will leave all those employees whose last name is not Smith, and it will only give those employees whose last name is Smith. This reduces our search time and also increases the efficiency. You can also create indexes on multiple columns. Like you can create composite indexes if your query frequently involve conditions on multiple columns together. Let's take an example. So you do is create index. Let's say you create index and index full name on employee. Then you can also provide, like, you only need a specific attribute. You only need like first name, or you are creating the index on last name. What this do is this create a composite index. So what it is doing is it is creating a composite index. What do you mean by composite index? Like we are creating index on two attributes, like first name. Also we are creating the index on last name as well, which can be useful for query that search or sort based on the both column. Like if we want to search or sort based on both the columns, we want to search or sort based on first name, last name. So composite index is the solution. Now let's look more about how do database indexing works. So the first is index creation. the database administrator. Remember, database administrator is the one who creates an index on a specific column, or we can say set of column, which was like composite index that we have seen. And then the second step is index building. Now index is created. Now we are going to build the index. So the database management system builds the index by scanning the table and storing the value of the indexed column along with a pointer to the corresponding data. Like we have discussed, we were having key and this was the pointer. There are something key and something pointer associated to that. This is what happening in the index building. Now then after index is built, we have query execution. When a query is executed, the database engine checks if an index exists for a requested column. Like if I am searching for A, it will go to the key, right? And if it is available, then it will go to the pointer, and if it will check like whether it is pointing in the table to some record, right? And if it is pointing to that record, it means the data exists and like the index exists for the requested column, so the query will be executed. But if it doesn't exist, the query will not be executed. After the query executed successfully, we are going to do the index searching. If an index exists, the database searches the index for the requested data. So using the pointers, so we quickly locate to the data. Like for example, I have taken example of XYZ, which was like, let's say this is a student and we are searching for the name, right? So it will directly go to that index. It will directly go to that index. Let's say this is first row, second row, and third, and here the XYZ is present. Here the data is present. So it will directly go to 3, right? And then we have the data retrieval. So the database retrieves the requested data using pointers from the index. This is what data retrieval is. I hope you got this point. Further, let's talk about the benefits of the database indexing, how it is beneficial. Like it is good for faster query performance. Indexes can significantly improve the query performance, especially for large data sets, by reducing the amount of data that needs to be scanned. Like we have taken the example of book. We already took an example of the book, right? So we need a table of content in the book to go to that particular page, to find the page number. Let's say you are having a book of 1000 pages. So it is very bad to go to each and every page to find that word, right? What you will do is you will simply go to the table of content. You will simply go to the table of content and you will find that index or page number and you will go to that page directly. So reduced CPU usage. By reducing the number of rows that need to be scanned, indexes can decrease CPU use and optimize resource utilization. What it is saying is like you are reducing the CPU utilization. Like we have put here a where condition. So with the help of where condition, you can simply put like those which are having a particular condition. Like let's say you are searching in the voter list and you are putting an condition age greater than or equal to 18, right? So these are all eligible voters, right? So you are reducing the time of searching and optimizing the CPU usage. Rapid data retrieval. Indexes enable quick data retrieval for queries that involve equality and range condition on the indexed columns. And then we have efficient sorting. So indexes can also be used to efficiently sort data based on the index column by eliminating the need for the expensive sorting operations. And we can also do better data organization. Indexes can help maintain the data organization and structure, making it easier to manage and maintain the database. Now let's talk about some types of database indexes. First, we will talk about indexes based on structure and key attributes. The first one is primary index. So why we are talking about structure and key attributes? We are actually talking about the schema. based on the schema, based on the key attributes, we are going to do this. First is the primary index. So in primary index, we automatically create when a primary key constraint is defined on a table, like ensures uniqueness and help with super fast lookups using the primary key. Actually, we have the primary key here, right? This is some primary key. So based on behalf of this, it is created here itself. Like this is the primary key, this is associated with some record, and this is also a primary key. So let's say this is indexing 1, 2, and this is 3. So based on the primary key, we are actually creating the index at the same time. So it is created on behalf of the primary key attribute. And then we have clustered index. It determines the order in which data is physically stored in the table. And a clustered index is most useful when we are searching in a range. So whenever you are searching in a range, let's say this is a record, right? This is a particular record, and you are just searching here. You are not searching the entire table. You are searching a piece of record. Then you need clustered index, right? So only one clustered index can exist per table. Yeah, that is also true. Only one clustered index can exist because we have a one range. There only we can search, right? And non-clustered or secondary index, this index does not store data in the order of the index. It is not storing the data in the order of index. Instead, it provides a list of virtual pointers, or we can say it is providing references to the location where the data is actually stored. So it is not the actual index. It is not the actual index like we are seeing here. This is an index, this is an index, this one is also an index. This is also a range of index. Let's say this is 12 and this is some 12th row, and this is some 14th row, right? This is a range in terms of clustered index. Non-clustered or secondary are not like that. These are virtual pointers which are pointing to the actual storage location in your database. So these are actually pointing to the actual storage location in the memory in the database. Now let's talk about the further types of database indexes. The second one is indexes based on data coverage. So we have dense index and we have sparse index. Dense index has an entry for every search key value in the table. It is suitable for situation where the data has a small number of distinct search key, and when fast access to individual record is required. So what does it actually mean by dense indexing? Dense indexing means like you are having the key and you are having the pointer, right? And you are having some table, you are having some record here, you are having some pointer, right? And you are having some corresponding keys. So each pointer is pointing to, like it is pointing to others, it is pointing to this as well, it is pointing to this as well, it is pointing to this. It is a dense network. So each pointer, there is a many to one relation, right? There is a many to one mapping, so that using a particular pointer you can go to the entire table and you can search for every record. This is dense index, and you can access individual record very fast. If I talk about the sparse index has entries only for some of the search key values. It is suitable for situations where the data has large number of distinct search keys value. Now let's talk about the third type of database indexes, which is specialized index type. Specialized index type. The first one is bitmap index. Bitmap index is excellent for columns with low cardinality, few distinct values, and common in data warehouse. The second is hash index. So index that uses a hash function to map values to specific location. It is great for exact match queries. The third is filtered index. Index is a subset of rows based on a specific filter condition. It is useful for improved query speed and commonly filtered columns. Let's talk about the covering index. Covering index includes all the columns required by a query in the index itself. So it is eliminating the need to access the underlying table data. Then we have function based index. So indexes that are created based on the result of a function or any kind of expression is applied to one or more columns of the table. Then we have full text index. If I talk about the full text index, an index designed for full text search, allowing for efficient searching of text data. Like when you type in the search bar, you go to the Google and you type www dot some site name. Let's say you are typing WordPress, for example. So that is index designed for full text search. And then we have a spatial index. We have used for indexing geographical data types. Now let's talk about what data structure indexes use. What are the data structures that we use? So most commonly used data structures which power the indexes are, we use b-trees, we use the hash tables, and also the bitmaps. Let's talk about them further. So how do we use b-tree? How do we use the balance tree? Most database engines use, like, either they use b-tree or a variation of b-trees like b+tree. B-tree have a hierarchical structure. They have a parent to child structure, right? They have a hierarchical structure with a root node. This is actually the root node. This is the root node here, right? And internal nodes, these are the internal nodes. We also call them as index node. These are also called as index nodes. And leaf node, we can also say that they are also leaf node. So each node in the B tree contains a sorted array of keys and pointers to the child nodes. These are the pointers. The blank spaces, as you can see, these are the pointers. These are pointing to the child node. These are actually pointing to the child node. And the sorted values, like sorted in sense, we have 10 here, then we have 15 here, we have 21 here, here is 3, here is 6, here is 12, then we have 24, we have 27, all are in sorted order. So here is why they are so well suited, like self-balancing. The first is self-balancing. So the first is self-balancing. These are actually self-balancing because B trees ensure that the height of the tree stays balanced even when inserting or deleting the data. Even if you are inserting a data, even if you are deleting the data, the height will always be balanced. This is the height. This is the height actually. This will always be balanced, right? So this ensures logarithmic time complexity for insertion, deletion, and searching. And then we have ordered. These are ordered. How we can say these are ordered? So B trees keep the data stored, making range queries, find all orders between date. Let's say you are having a date X and you have date Y. You are searching the data in between, and inequality comparisons very fast, right? It is disk friendly as well. This is the property, like these are disk friendly. How these are disk friendly? B trees are designed to work well with disk based storage. So a single node of B tree often correspond to disk block. This is often corresponding to a disk block. That's why we can say these are disk friendly, and these minimize disk access operation. So how these are minimizing disk access operation? If I go to this node, I will simply go to that disk where the data is stored, right? So I am minimizing the time. Many databases use a slightly modified B-tree variant, which is also called as b+tree. In a b+tree, all the data values are stored only in a leaf node, which can further improve the performance for certain use cases like range query. Now let's talk about the hash tables. Let's talk about the next data structure, which is hash table. Hash tables are used for hash index, which are based on a hash function. So let's say there is a search key and the search key goes to the hash function, right? Based on the search key, you are putting a hash function. Let's say it is giving you a value of 6, then you are pointing to the pointer to the row 6, right? It is giving you a value 6 and you are pointing to the row 6. Then you directly go to the row 6 and search for the data. You are directly going to the row 6, right? And you are searching for the data. This is how the hash function actually works. A hash table consists of an array of buckets. These are an array of buckets actually, with each bucket containing the address for rows in the data. These are having the address of the row. These are the rows, right? These are the all rows. These are the actual buckets which are pointing to the row. Let's say this is pointing to row 5, right? And this is pointing to address of row 7. Let's say we have here something and it is pointing to row 1. So these buckets are actually storing the address of these rows in the data table, right? Hash indexes employ a hash function. These are using actually a hash function to map keys to their corresponding bucket in the hash table, enabling constant time lookup operation. And hash indexes provide fast equality lookups, as the hash function determines the exact location of the data based on the key. And however, the hash indexes do not support range queries or sorting efficiently. We cannot say that it is most optimal, but we can say that it is optimal. Like, it is saving our time. Like, based on the search key, here the D3 search key came, we put some hash function on it, and it is providing us the value 6, which is the location of the row 6, right? Now let's talk about the bitmap. This is another type of another category of data structure that we use. Each bit in the bitmap correspond to a row. So each bit in the bitmap is corresponding to actually a row. It is corresponding to a row, right? And the value of the bit indicates whether the key value exists in that row. The value actually indicates whether the key value is existing in that row or not. So bitmap index use a bitmap. It is a binary array. So it is actually a binary array, right? These are in the form of arrays. And to represent the presence or absence of a specific key value in each row of the table, bitmap indexes are well suitable for columns with low cardinality. Remember, these are best suited for those columns with low cardinality and a small number of distinct values, and for performing complex queries involving multiple conditions. Bitmap operations, like you have, what are the kind of bitmap operation that we use? We have AND, we have OR, we have NOT, right? These are the bitmap operation we use to perform. So these are performed efficiently using bitwise operation, and making bitmap indexes suitable for analytical query involving multiple columns. At last, let's talk about how to use the database indexes, how we can use them. So first of all, identify the query pattern. What you have to do, you have to identify the query pattern. So analyze the most frequent and critical queries executed against your database. What are the kind of query you are executing against your database? Based on that, you are going to identify a pattern, right? And to determine which column to index and which type of index you are using. There are so many index that we have discussed. So out of those, which kind of index you are using, based on that, we will identify first the query pattern, right? And then we will find the index frequently used columns. So consider indexing columns that are frequently used in, like, you have the where condition, you have join condition, then you have order by. So based on these clauses, you are going to consider indexing columns, right? So you are going to identify frequently used columns and index about them. And then we have index for selective columns. Then we have, like, indexes are most effective on columns with a good spread of data values, high cardinality. Indexing a gender column might be less beneficial than one with a unique customer ID. So indexing a gender column, what it is saying is, like, if we are having a unique customer ID, right? unique customer ID is more beneficial. How it is more beneficial? Because we are actually creating the primary key here, and if we are having gender, there can be multiple male, multiple female, right? So it is not that efficient, but we can go to a particular record based on the customer ID. And we use appropriate index type, like we choose the right index type for your data in query, the type of index you choose. After that, consider composite indexes. Also consider the composite index while using your database index. So for query involving multiple columns, let's say your query is involving multiple columns. You are having multiple columns, right? You are having multiple columns. Consider creating composite index that encompass all relevant columns. So it should encompass all the relevant columns, and this reduce the need for multiple single column indexes and improves the query performance. And monitor index performance. This is very important. Regularly monitor index performance, remove all those unused indexes, and adjust your indexing strategy as the database workload evolves. Also avoid over indexing. Over indexing is also not good. It makes our database more complex. Avoid creating too many indexes, right? As this can lead to increased storage requirement and a slower write performance. So when you are actually writing something in your database, you can retrieve the data very easily based on the index. But when you are actually writing, so you are making it more complex because it need more storage requirement, right? Maybe your index is mapped to so many records, so that is creating a complex task, right? So indexes take up extra disk space since they are additional data structures. They are actually the additional data structures which are using extra space, because we are using b+tree, b+tree, right? And we are using hash map, so we are actually using extra data structure. So these need to be stored alongside your tables, right? And every time you insert, update, or delete the data in a table with an index, the index needs to update too. If you are updating the data, the index is also required to be updated. Because let's say index 1 was pointing to this, right? Now someone came and I have updated this. So this will also update the index in return. I hope you got my point. This can slightly slow down the write operations. Okay guys, this was all about today's video. I hope you like this video. Do like, share and subscribe my YouTube channel. Do mention in the comment section which part you didn't got, and if you have any question, do mention in the comment section. You like everything and you understand all the concepts. We'll see you in the next video. Thank you.